Hi, I'm Rob Elshire, President of the Charitable Society Genomics for Aotearoa, New Zealand. I'm looking forward to showing you the work that we've been doing on our public bioinformatics platform. One of the great things about going at the end of a conference is you get to reference the great talks that were done previously in the conference. Yesterday, Steve Manos did a great job of describing the kind of current state of play in scientific computing in regards to the use of containers and the orchestration engine Kubernetes. It's my pleasure today to show you an implementation of the things that Steve described yesterday. Before I get started on the demonstration, I just want to thank some people that were instrumental in getting this all together to work and working. The first one is Bruno Lago, who I met at the eResearch conference in 2014, long before there was a Catalyst Cloud and before Bruno became the CE. He and the Catalyst Cloud have been instrumental in supporting, not only supporting the work that we're doing in cloud computing, but actually working side by side with me to make it all go. Another person that I've been fortunate to learn a lot from is Finlay Thompson, currently the CEO of Dragonfly Data Science. Finlay and Dragonfly have been doing end-to-end reproducible workflows for many, many years. And it's through conversations with him that have really helped me understand the nature of the problem. On the right-hand side, we see a couple of iterations of the Palmerston North Bioinformatics meeting. On the top, one of the more early years, and the one on the bottom, just this last year. We've been going for 5 years, and a lot of the discussions that we've had over the years in that group have influenced the defining of the nature of the problems and the work to be done in doing reproducible bioinformatics. And then, of course, you see all the logos of these great free software projects that make all of this work possible. This slide gives a schematic overview of the GFANZ bioinformatics platform. It has the collaboration platform, the tool repository, orchestration, and graphical interface. We're working on all of these parts simultaneously, and I won't go into detail with this slide. Rather, I'm going to show you how they work. Let's begin by giving a demonstration of the system in action. What we see here is the graphical user interface for Argo. It's presented via a standard desktop browser. The dataset that we're using for our demonstration today is from the Kiwi Whakapapa project. This is an affiliate project of GFANZ. You can find out more about that project on genomics.nz. Okay, let's submit a new workflow. We're going to click on this to edit a workflow, and then just upload the Kiwi Whakapapa fast structure YAML file. This particular workflow only has 3 steps. Download the data, check that the data is there, and then run the program fast structure. So we'll click on Create, and it will start running. And we'll see that it will run through all of the steps, and we'll come back to that in a minute. This simple 3-step linear workflow has completed. Argo also supports directed acyclical graphs. Argo workflows can scale massively, utilizing the underlying Kubernetes infrastructure, which we will describe next. Here we're showing the setup of a Kubernetes cluster in the Catalyst Cloud. On the left-hand side of the screen, you see the browser-based graphical user interface at the Catalyst Cloud. On the right, you see our command line that we're using to set it up. This is a very simple Kubernetes cluster, but it's enough to install and run the Argo software that we showed in the last step. A little bit of an explanation around how all these pieces work together. You can think of Kubernetes as a conductor in an orchestra, and the Argo workflow as the piece of sheet music. Those two things, along with the musicians and instruments, which would be represented by the Docker containers, work together to essentially set up enough compute, the right tools, and the instructions to perform an orchestra piece. So this is how they all work together. To store, archive, and distribute our Docker containers, GFANZ uses Docker Hub. We have just recently received open source project status with Docker Hub, which allows us to keep our containers there in perpetuity and to be downloaded as many times as people might like. This helps meet the goals of being able to have a repository for reproducible research. You can see that we have at the moment 17 repositories. It's very easy to make more, and we'll see how that's done a little bit later in the talk. Let's take a look at Structure Threader, which is the example tool we used with the Kiwi Whakapapa data. Every Docker container that GFANZ creates using its infrastructure has a set of metadata that goes along with it. That metadata includes the tool name, the version, the citation, documentation, source code, and license. We had also put a link to the wiki on how to use our Docker containers here in the Docker Hub page, so that people that are finding our tools this way can find out how to use them. While GFANZ intends to have a fully automated reproducible workflow system using Argo and Kubernetes, other people may want to be able to use the Docker containers individually. They can do that by using the docker pull command that we see here on the screen and running it manually. Okay, let's come back to the main repository page and talk about specific versions of Docker containers. So in order to have a reproducible research chain, you need to know exactly which Docker container was used. So in each Docker container has the potential of having multiple versions based on finding bugs or improvements in the software contained in it. So Miraculous is one example. Let's click on that. Okay, this has the same kind of information that we saw before with Structure Threader, but in addition to that, we can click on the Tags tab. And we'll see that there have been multiple Docker containers made for Miraculous over time. And you may have used a specific one in your own research. And the most recent one is always called latest. So that's whatever the most recent one is. But it doesn't necessarily, that may change. So latest isn't the best way to identify the Docker container that you're using. It would be more appropriate to use something like this that has the version and an extra ID on it, so we can be very clear exactly which Docker container was used. So this allows, again, for reproducible research, but also an audit trail for the analysis itself. So in our example tool use of Structure Threader, we only had one version of the Docker container in Docker Hub because we only did it one time. Now we're going to do this again, creating a new Structure Threader Docker image by making a trivial change in the source code and using our continuous integration, continuous deployment system at GitLab. Then we'll come back to this page and show that it is indeed got a second one. On the left, we see the GFANZ GitLab repository. On the right, the command line window for my local computer. So what we're going to do is create a new Docker container for Structure Threader by making a trivial change to the code in the Structure Threader tool folder. So we're going to follow these instructions, but we've already done some of it. So we've already cloned the Git repository locally, and we already have the tools in the tools folder. So if I just do an ls, we can see that there are some tools in here. I'm going to go to the Structure Threader folder, see what's in there. Okay, so I'm not going to go through all of the bits and pieces for this, for the way this all works. That's documented online, and I'm happy to answer questions later or provide assistance. But we'll go down to number 3 here. We're going to do a create new branch. So I'm going to do a git checkout B for branch, and I'm going to just call this Structure Threader. So I've switched to a new branch. So if I hit type in git branch, it tells me that there are 2 branches currently, and the active one is Structure Threader. So Typically, we would create a new directory with a tool name and copy the templates folder and then edit some things to create the code necessary to create the Docker container. However, in this case, we're just going to make a small change. So I'm just going to go to the, let's do something super simple, the README MD file, and I'm just going to insert a space, a space after that license. So it's a very small change, not even noticeable, right? When we're done, so we've made the change, and I'm going to type git add dot at git commit, which you'll see in step 7 here, and hit enter, and I'll just try this as a trivial change to push a Docker image. Okay, and then I'll write it out, and then exit, and then follow the next step here, which is, I'll just clear this, get back up at the top, git push set upstream origin, and we call this structure threader. Okay, so we click on that. That's been done, and then I should be able to click on this link here to see what pipelines have been in, and you'll see that here's the one that I've just added. It says trivial change to push a Docker image, which is what I typed in over here. And what's happening now is the GitLab continuous integration, continuous deployment system that we've set up picks up that change. And what it does is it does several steps. It's building the Docker container, and we can click on that. Click on this, and we'll see that it's got 2 stages. It's running the build, and then and it will also test the install to see if the tool that we installed is accessible and just runs. Okay, we can see from here that the change that I made passed the build and test phases. And one key thing to note is that the CI/CD system is set up so that it will only run through creating Docker image and testing it for the tool that has been changed. It doesn't run through all of the ones that exist in the repository, only the one that has been added. Okay, we're going to click on the Create Merge Request button. So I'll click on Submit Merge Request now. That was the request. And then typically, like I say, someone will review the code and then just click on Merge. This change has opened a new pipeline that allows a build, a test, and a deploy. All 3 stages of the CI/CD pipeline have completed. Let's hop on over to the Docker Hub repo and check to see that our new Docker container is there. So this is the GFANZ structure threader Docker repo page, as it was before we pushed out the latest Docker image. I should be able to just hit refresh, and we will see that the new one's there. And there we go. The latest one is pushed out 6 minutes ago. That's it for today's demonstration. Thanks for watching. We're GFANZ, where society and genomic science meet. Visit us at genomics.nz for more information and to join.